Okay, limiting reactants. So basically, here's the idea. If I want to make a cheese sandwich, I need 2 pieces of bread and 1 piece of cheese, and I get a sandwich, cheese sandwich. Now, it's not like a great sandwich. It's a very simple sandwich, but for this illustration or this discussion, I think it's going to be fine. So look at, if I had 100 pieces of cheese, how many sandwiches could I make? Right, 100 sandwiches. If I had 50 pieces of cheese, I could make 50 sandwiches. What if I had, now, what if I had 100 pieces of bread? How many sandwiches could I make? I could make 50 sandwiches. Why? Because each sandwich takes 2 pieces of bread. Now, I know you're probably like, this is really silly. Why are we talking about this? Because if you understand this concept, you understand limiting reactants. So if I told you I have 1,000,000 pieces of bread, I have 1,000,000 pieces of bread, and I have 3 pieces of cheese, my question is, how many sandwiches can we make? The answer is we can make 3 sandwiches. Why? Because we're limited by the cheese. We have plenty of bread, excess reactant, but we're limited by the cheese. This is the limiting reactant. It's the same thing in chemistry, except instead of using bread and cheese and sandwich, you would use one certain compound, another compound or element, and make a product of some type of compound. That is the whole thing. Now, here's how we actually would do that if we were going to use our dimensional analysis. Here's a few questions. Let me erase this stuff here. Okay, so if I said you had 50 pieces of cheese, how many sandwiches you could make? Well, we could use the coefficients of this chemical or this recipe to go, okay, well, I have 50 pieces of cheese. I know this is silly, but bear with me. Times fraction bar, bring down the cheese, and go to sandwiches. Now, what do I put down here? 1 piece of cheese. What do I put up here? Makes 1 sandwich. 50 times 1 is 1, and 50 divided by 1 is 50. So I can make 50 sandwiches. This is just a very long way of doing something that we can really do easily in our head. But understand that this is the way we're going to do these problems when they get more complex. And again, with 100 pieces of bread, then you understand that if I were to do the experiment or do the reaction or the recipe, bring down bread, and I'm going to sandwiches, right? Notice that I want to compare on making the sandwiches. I want to compare making a product. So according to our recipe, 2 pieces of bread makes 1 sandwich. I'm going to give you a little hint here. When I'm cooking pancakes or whatever, and let's say we have the family over and there's 17 people at the house, and the recipe says you can make this much for 6 people, let's say. I can use these same techniques to know exactly how many cups of pancake mix I've got to mix, and everybody wonders how I do it, and what they don't know is that I'm just simply using these dimensional analysis tools that we're practicing here today. So okay, so 100 divided by 2 is 50. I can make 50 sandwiches. So I don't know if that's the way you even spell sandwich. So look at this. This would be the perfect reaction or the perfect thing. We would have no excess, right? If we had 50 pieces of cheese and 100 pieces of bread, we're not left over with anything. Nothing's limiting us and nothing is in excess. Everything's working out great. But that's not often the case, right? A lot of times we have more of one thing than another. And then this is where we have to understand the concept of a limiting reactant. I'm not using chemicals because sometimes people let the letters and stuff distract them and psych them out, and then they don't think they can do it. But trust me, you can do this. So again, remember, if we have 100 pieces of bread, and let's say we have 20, or let me make some, well, no, we'll just do 100 pieces of bread, and let me make some more interesting problem here. What if we have 72 pieces of bread? We have 72 bread, and we have 4 pieces of cheese. Which one's the limiting reactant? That's easy, right? Cheese is the limiting reactant. How would we do this if it was complicated and we couldn't understand? We would follow the same structure. We put down bread here. We would go to sandwiches. Now it's important, we got to think in terms of a product. I can't put bread here and go to cheese. I have to think in terms of the product. So 2 breads make 1 sandwich. So that's going to be 35.5. So I can make 35.5 sandwiches here. And here, times fraction bar, bring down the cheese. Notice I'm going to go to the sandwich. I'm not going to use bread here. Sometimes people get confused because they're not using a product. You always got to try to make the product and compare. So 1 cheese is 1 sandwich, so that means 4 sandwiches. Apologize for that. 4 sandwiches. Okay. So which one is the limiting reactant? It's whatever reactant made the least amount of sandwiches. So check this out. This reactant here made the least amount of sandwiches. This is the least amount of sandwiches. Therefore, I can say that the cheese is the limiting reactant. Cheese is the limiting reactant. Limiting reactant. And we would call the bread, we have plenty of bread, we would call the bread the excess reactant because there's plenty left over. Now we're going to extend this to chemistry, and we're going to look at a real chemical reaction, and we're going to do the same thing. It's no different than what we just did. It's just using a real chemical reaction. So let me get us set up for that real quick here. Okay, here's a real reaction. Now we're not talking about sandwiches. Hopefully that was helpful to just give you the general idea, but here's a reaction that's used in the space shuttle main engines, or at least was used. You have hydrogen here, you have oxygen here. Actually, it's liquid hydrogen, liquid oxygen in the tanks, but basically it's vaporized, it's turned into gas in the engine as it becomes water. And so now let's do a problem, a limiting reactant problem, where I will tell you, what if we have, let's just do something that would be like space shuttle size amounts. Maybe it's a lot more than this, I don't know. Let's say we have 2,345 kilograms of liquid, or of hydrogen. We'll just say it's hydrogen gas. And we have 1,350 moles of oxygen gas. Which one of these is the limiting reactant? How would we find that out? Which of these is going to limit our reaction? And hinder us in terms of how far our space shuttle can go? Well, here's how you do it. You do it the same way we did the cheese sandwich problem. You convert each of these things into an amount of product. And it's probably easiest to just convert it into moles of the product, even though you can convert it into grams of the product. It doesn't really matter. You just want to have the same unit for each calculation to see which one makes less. So let's give that a try. So go ahead and do your stoichiometry. And we're going to go to grams of hydrogen gas. And then we're going to go from bring down grams of hydrogen gas, and then we're going to go to moles of hydrogen gas. Go to moles of hydrogen gas, and where should we go now? Right, moles of H2O, moles of the product. Now in some problems you might have 2 or 3 products. Just pick one and use the same product for both mole problems that you do. So we're just really doing 2 mole problems here, and we're seeing which one equates to the least amount of product. Okay, so we'll go back here, and we know that there's 1,000 grams and a kilogram. This was probably not a big enough number, but we'll just go with it. And that 1 mole of H2 is actually 2.02. Why? Because we're talking about H2. We're not talking about 1 hydrogen. If it was 1 mole of H, that would be 1 gram of H, or 1.01 grams. But since it's 1 mole of H2, 1 mole of H2 has a mass of 2.02 grams. Now we look at do you remember what they're called? Our coefficients. And here it says that 2 moles of hydrogen gas make 2 moles of water. So we'll put a 2 here and a 2 here. Okay, let's set up this problem. Bring down your moles of oxygen. This one's actually going to be very easy. Where should we go to now? We can go right to moles of H2O. We look at our coefficients. 1 mole of oxygen, according to the balanced chemical equation, makes 2 moles of water. We're done with that one. So let's see, that's 2,700 here. 2,700 moles of H2O. That's the amount of product that we can make with this amount of moles of O2, or this amount of cheese, if you will. And this one, I got to use the calculator, so let's go ahead and do that. So 2, 3, 4, 5 times 1,000, enter, divided by 2.02, enter, times 2 divided by 2. It's just really multiplying it by 1, so I don't really need to input that. And we end up with a very large number, 1,160,891 moles. 1,160,000. Yeah, 891 moles of hydrogen gas, or the bread. So, I'm sorry, not hydrogen gas, H2O. Got to be careful. See, this is the unit that I'm ending in. So, the oxygen we started with makes this amount of water. This amount of water. The hydrogen we started with makes this amount of water. Which one is limiting us? That's right. The oxygen is the limiting reactant. So we often just abbreviate that by doing LR. That's the limiting reactant, oxygen. And then we can call this one the excess reactant. And that's how you determine the limiting reactant. You do a couple different mole problems, and whatever makes the least amount of product, again, you have to make sure it's the same product. If you have multiple products, we were using H2O. Oxygen made less H2O, so it's the limiting reactant. And we have excess hydrogen when this is all done. Hope that was helpful, and please practice your problems, and see you next time.